Hello everybody, hope all of you are well, and today I will continue the chapter organic chemistry. So first we will discuss diastereoisomer. Diastereoisomers are the stereoisomer that do not have a mirror image relationship. They have different physical properties. Diastereoisomers can be separated by physical methods like fractional distillation, etc. Okay. Like if we think about the active tartaric acid and mesotartaric acid, okay, there will be no mirror images and they will be pair of diastereoisomer. Next we will discuss meso compound. A meso compound is one whose molecules are superposable on their mirror image even though they contain chiral carbons. A meso compound is optically inactive because it has a plane of symmetry which divided the molecule into two equal halves. The rotation caused by the upper half portion is compensated by the lower half portion and the net rotation is zero, and this phenomenon is known as internal compensation. If we think about the mesotartaric acid, if we draw the structure, you can understand. This one is the structure of mesotartaric acid. So here it contains two chiral centers, this one and this one, but there is one sigma plane of symmetry. So because of this sigma plane of symmetry, it will divide the molecule into two equal halves. One half is the mirror image of the other. Okay. Next we will discuss the calculation of number of stereoisomers. Number of stereoisomers, both optically active and inactive, can be obtained from the number of chiral centers present in the molecule. Molecules contains n number of dissimilar chiral centers and cannot be divided into two mirror images. Okay. Then number of optically active isomer will be 2 to the power n, and number of this optically active and number of meso will be the 0. Okay. So this is meso and this is optically active. Now in this case we can think about the example of lactic acid. So if we think about the lactic acid, COOH, HOH and here CH3. Okay. So this is the structure of lactic acid. So here it is not divided by two equal half and number of chiral center will be 1. So 2 to the power 1 means 2. So this will be one structure and its mirror image will be another structure. So there will be two optical active isomer and there will be no meso isomer. Understand? Next, molecules containing even number of chiral center and it can be divided into two mirror images. Then optically active will be 2 to the power n minus 1, where n is the number of chiral center, and optically inactive will be 2 to the power n minus 2 by 2. That will be the meso isomer. Okay. Here we can think about the example of tartaric acid. Okay. So tartaric acid, COOH, CHOH, COOH. So in this case, the molecules contain even number of chiral centers and it can be divided into two equal half. Okay. So definitely the number of two chiral centers is present. So it will be 2 minus 1, that means 1, 2. So optically active compound will be 2, and here it will be 2 minus 2 divided by 2, that means 0 by 2. That will be there 0, 2 by 0 means 1. So meso will be 1. Okay, just now I have seen it. Okay. And next another type is there that molecules contains odd number of chiral centers and it can be divided into two mirror image halves by a plane passing through the central or chiral center. Okay. So here the number of optical active isomer will be 2 to the power n minus 1 minus 2 to the power n minus 1 by 2. Okay. So this will be the optically active and meso will be 2 to the power n minus 1 by 2. Okay. So here we can take one example like CH3, CHOH, 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 CH3. So in this case, total number of chiral center is 3. Okay. So that will be the 3 minus 1. That will be the 2 to the power 2, and here also 3 minus 1 by 2 to the power 1. So from here what number we are getting, that is 2. So if we put here 3 to the power 3 minus 1, okay, minus 2 to the power 3 minus 1 by 2. So that means 2 to the power 2 minus 2 to the power 1, that means 4 minus 2, that will be 2. So number of optical active isomer will be 2 and number of meso isomer will be also 2. Okay, so in this way this type of calculation is very much important for your exam. So you have to practice. Okay, that is the calculation of stereoisomer, how many is optically active and how many is optically active. So in this way I have completed this stereochemistry part. Next we will go to the type of reaction mechanism. In case of organic reaction, okay, an organic molecule reacts with an appropriate attacking reagent and leads to the formation of one or more intermediate, and finally to some expected product with maybe there are some side product also. And the sequence of steps through which a reaction is supposed to take place is called reaction mechanism. Type of reaction mechanism in organic chemistry, okay, are generally two types. One is concerted mechanism, another is non-concerted mechanism. Okay, so reaction mechanism in which the breaking and making of bonds takes place simultaneously without formation of any intermediate is called concerted mechanism. So here if we show you, then you can understand this is the energy and this is the reaction coordinate. This will be the starting material and this will be the product. Okay, so there will be no intermediate. Graph will be like this. So this is for concerted mechanism. Okay, and reaction mechanism which proceeds through the formation of intermediate before the product formation or before the products form, okay, is called the non-concerted mechanism. Definitely in case of non-concerted mechanism there will be some intermediate. So in this case this is the energy and this is the reaction coordinate. So you will get a intermediate like this. This is the reactant and this is the product. So this one is the intermediate. So definitely there will be intermediate. Next we will discuss electron displacements in organic compounds. There are 4 types of electron displacement mechanism generally observed in organic molecules. One is inductive effect, another is electromagnetic effect, another is mesomagnetic effect or resonance effect, another is called hypervolution. Now inductive effect, the permanent displacement of the shared electron pair in a carbon chain towards the more electronegative group is known as the inductive effect. Suppose if we attach one electronegative group in a carbon chain, what will happen? This is the carbon chain. This is the electronegative, so it will be delta negative, it will be delta positive. Okay, it will be delta 2 positive and this is delta 3 positive. After the carbon 3, the inductive effect will be 0. Okay, so here this one is the higher. This one definitely will change the pulling of this X. Okay, actually X is more electron, it will pull the attract the bonding pair electron towards itself, so it will become delta negative and charge will slowly decrease and the pull will also decrease. But if we attach a metal atom, then what will happen? Just the opposite. So metal will be delta positive, this will be delta negative, this will be delta 2 negative, this will be delta 3 negative. Like this it will decrease. Okay, so this is the permanent effect. Okay, inductive effect is simply I effect, and there may be 2 type of inductive effect. One is plus I effect, another is called minus I effect. So when we attach some group like this electronegative element, so that will attract the bonding pair electron towards itself. Definitely they are called minus I effect. So if a group is more electronegative than hydrogen, then the group withdraws the electron from the carbon chain towards itself. Okay, and it is said to have plus I effect. It is said to have minus I effect. But in case of plus I effect, if a group is attached to the carbon is less electronegative than hydrogen, it donates electrons to the carbon chain and it is said to be plus I effect. Now inductive effect is permanent and irreversible. The electron displacement progressively decreases along a carbon chain as the distance from the carbon atom directly attached to the substituent increases. Okay, and inductive effect is almost negligible after the 2 carbon atoms. Okay, after 3 carbon atom it will be nil. Okay, and different group cause polarity to different extents. Okay, in your book there is some order of minus I effect that you will read, and the order of plus I effect. Generally, in case of ammonium, the minus I effect is the highest. Then there will be nitro, then cyanide, then sulfonic acid, then carboxylic acid, then fluorine, bromine, iodine. Then there is waste, then there is ether, then phenyl, then hydrogen. And in case of plus I effect, generally tertiary alkyl group has the more inductive effect, plus I effect, then secondary, then primary, then methyl, and then hydrogen. So in this way it will decrease. Okay. So next we will discuss the application of inductive effect. If we think about the CH3Cl molecule like this, so this molecule is polar, okay, and it is more reactive compared to the methyl. Because this inductive effect of this minus chlorine group, chlorine is more electron, it will attract the bonding pair electron towards delta negative, it will be delta positive, and because of this polarity, it will be more reactive. In case of SN1 reaction, we know that because of inductive effect, okay, the positive charge will be stabilized. So tertiary halide has better reactivity compared to the secondary halide than compared to the primary halide. So when it will form the tertiary carbocation, because of the three methyl group plus I effect, it will be stabilized. So tertiary carbocation is more stable than secondary carbocation, then the primary carbocation. Hope you can understand. But if we think about the anion, generally tertiary carbon ion is less stable, okay, and this one will be the most stable, and this one is the highest stable, okay, and then we can write that CH3 minus. So stability is increasing, and here the stability is decreasing. Then there will be CH3 plus. So CH3 plus is less stable. Okay, so here plus I effect destabilize the negative charge. Okay, that means carbon ion. Oh, that is why it is very much less stable. But here there is no plus I effect in case of CH1, so it is stable. Okay, compared to these anions. Hope you can understand. And next we will discuss the relative strength of the acid and bases. The minus I effect increases the acid strength, and plus I effect decreases the acid strength. If we think about the formic acid and acetic acid, definitely formic acid is stronger acid than acetic acid, because here the methyl group of the acetic acid increases the electron density on this OH bond, and it will be resonance will be hampered, and it will be difficult to break the OH bond. So that is why formic acid is more acidic compared to the acetic acid. But if we introduce some electron negative group like CH2 chloroacetic acid, alpha chloroacetic acid, or acetic acid, okay, so in this case what will happen? In this case, what will happen? This alpha chloroacetic acid and acetic acid. So in this case, what will happen? That alpha chloroacetic acid is more acidic compared to this one. This alpha chloro, okay, and it will attack the bonding pair electron towards itself. Next one is the trimethylamine. Trimethylamine is a very good base because of the methyl group. Okay, will increase the electron density on nitrogen atom. Because of this electron density, it can donate the electron pair better. Otherwise, if we think about the CF3O3N, so this is a very poor base, and its donation property very much less, okay, or negligible, because this fluorine has minus I effect that will attack the bonding pair electron towards itself, so it will be very difficult for this nitrogen to donate this electron pair. Okay, so in this way, in different cases, we can use this inductive effect. Hope you can understand. And next we will discuss the electromagnetic effect. Electromagnetic effect, inductive effect is a permanent effect, but electromagnetic effect is a temporary effect. When the reagent is present, it will show that effect. So complete transfer of a shared pair of electrons of multiple bond to one of the bonded atoms under the influence of the attacking reagent is known as the electromagnetic effect. We can think about this carbonyl group. So here this will be delta negative, this will be delta positive, this is cyanide. So here it will attack. Okay. So in this way we can think about the displacement of this pi bond. Okay. And another example we can think about this carbon-carbon double bond. This is a non-polar. But in presence of hydrogen plus, there will be addition of hydrogen and formation of breaking of this bond, formation of the ethyl cation. Okay, so this is also the cause of the because of the electromagnetic effect. Actually, these effects comes into play in presence of attacking agent. Without attacking agent, there will be no such effect. This is a temporary effect. Next, we will discuss very important thing, that is the in organic chemistry, that is the resonance. In case of certain compounds, more than one structure can be written, but none of them is able to explain all the known properties of that compound. Okay, completely. The different structures written are as the resonating or contributing or canonical structure, and this phenomenon is known as resonance. The actual structure, okay, known as the resonance hybrid, and the energy which represents the stabilization of a molecule, okay, due to the resonance is called resonance energy. You can think about the benzene. I will calculate the resonance energy of benzene. It will be 36 kilocalorie per mole. Okay, next we will show you some rules how to shifting of electron in case of resonance. Okay, suppose there is one electron shifting, we will show in this way, this arrow. But if there is two electron replacement, then this type of arrow we have to show. Next, if the arrow goes on an atom, then it will become A negative. If the arrow goes from one atom, then it will become A positive. Okay, so in this way you have to two electron is present. So this two electron, if you go under, so it will become A positive. A positive. Okay. And when this arrow comes in between a bond, it will be a double bond. And when this arrow of a double bond come here, then it will become one side negative, one side positive, another side negative. So you can understand. And generally, there are four type of resonance or conjugation. Okay, one is pi conjugation. This is called pi conjugation. Okay. And next, there will be cation pi conjugation. This is the type of conjugation. And here we will show in this way, that shifting of electron in this way. Negative, and this will be positive. And next one is the cation pi resonance. This is the cation pi resonance. So here double bond will shift. We have to show in this way. Next will be the anion pi resonance. Okay. Next will be the non-bonding electrons and pi electron conjugation. So these rules, okay, you have to remember, and that you have to apply during the writing of resonance structures. I am showing you following this rule, the different types of resonance structure. So when there is alternative double bond and single bond like this, this system is called conjugated system. Okay, so here we can show the shifting of electron in this way. If we show the stepwise, okay, then there will be different, the number of canonical structure will increase. Okay, definitely it will be different, more number of canonical structures. Okay, suppose in a ring, like benzene ring, there is alternative double bond single bond. Definitely there will be two structures like this. So in this way we have to draw the resonance structures. Okay. Suppose in a ring there is negative charge. then we have to draw resonance structure in this way. Now, what will be the actual structure? Actual structure will be the resonance hybrid. Okay. So in this case, what will be the resonance hybrid in case of benzene? I can show you in this way. We will write the resonance hybrid. This is called resonance hybrid. And actually, the resonance energy is the energy difference between the actual structure. Okay, actual structure will be, suppose this is the energy level, this is the actual structure, and this is the most stable canonical form, and this energy difference is called the resonance energy. So this is the actual structure, this is the resonance hybrid, and this is the most stable canonical form. Hope you can understand. So this energy difference will be the resonance energy. Next, I will show you resonance for some groups, okay, that will increase the electron density, okay, in the pi system or ring. Okay, they are called plus R group or plus N group, and those will decrease the electron density or take the electron density from the benzene ring. They are called minus R group or minus N group. Okay, suppose if we give one OH functional group to the benzene ring, then it will increase the electron density inside the benzene ring. And the resonance structure will be like this. This will be negative, plus, next step, okay, and in the final step, what is happening? Okay, so these are the canonical structures, okay, resonating structures. The actual structure will be the resonance hybrid. And here it will be delta positive, and inside this is delta negative. Negative charge is rotating. Okay. So here what you are observing that the inside the benzene there is negative charge. So this OH functional group is increasing the electron density at the ortho and para position. Okay, of this benzene ring. Okay, that is why they are called plus R group or plus N group. And there are some groups like nitro, COOH, CHO that will decrease the electron density in the benzene ring. Like nitro group. Now in this case, the type of electron shifting will be like this. So these are the canonical structures of the nitro group, and the resonance hybrid will be like this. One negative charge is dividing. So these are the delta negative, and inside this positive charge is rotating delta positive. So this nitro group is decreasing the electron density at the ortho position as well as the para position. So this type of groups are called minus R or minus N. So if a group withdraws electron towards themselves, okay, through resonance, and then it is called minus R or minus N. Hope you can understand, and you have to practice the resonance structures. Okay, that is very important for your exam also, and many things you can explain, or many types of phenomena you can explain by using this resonance theory, okay, or resonance structures. Next we will discuss the calculation of resonance energy. Suppose if we think about the cyclohexane, and if we give hydrogen in presence of the platinum catalyst, okay, then there will be formation of cyclohexane, and the amount of energy here it will be released. It will be delta H is equal to minus 28, around 28.6 kilocalorie per mole. Now, if you take benzene ring containing 3 double bond, addition of 3 hydrogen molecule in presence of platinum catalyst, you will also get cyclohexane. And here the delta value, okay, that is the delta H value, enthalpy of formation, the heat of enthalpy of formation, that will be the triple of this value, that is minus 28.653, but actually it is coming minus 49.8 kilocalorie per mole. So if we think about the 3 cyclohexane, you have to multiply it by 3. So if you multiply it by 3, then you will get 85.8 kilocalorie per mole, and you are getting 49.8 kilocalorie per mole. So if you subtract, then you will get 36 kilocalorie per mole. So definitely the resonance energy, in this way we can calculate the resonance energy. Resonance energy for benzene will be 36 kilocalorie per mole. Okay, if I show you the structure, then you can easily understand. This is the energy diagram. Okay, and if this one is the resonance hybrid, this is the position of the resonance hybrid of benzene. This will be the structure of resonance hybrid like this, and this is the most stable canonical form. Like this. Then this energy difference. Okay, this one is called resonance energy. Hope you can understand. Now, relative contribution of resonance structures towards the resonance hybrid. There are some rules how to understand which resonance structure is most stable and which one is less stable. First one, you have to understand that non-polar structures are more stable than the dipolar structure. Okay, suppose in case of cyclobutadiene, or in case of 1,3-butadiene, if we draw the resonance structure, then there will be 2 resonance structure. One is the polar resonance structure, another is called non-polar resonance structure. Okay, so this is non-polar, this is polar. Which one will be most stable? Definitely the non-polar will be the most stable. Next, there is rule 2. Resonance structures with greater number of covalent bonds are more stable and contribute more towards the resonance structure or resonance hybrid. Okay, suppose if we think about CH3 C double bond O plus. So in this case, if we draw the resonance structure, then you can understand CH3C triple bond O plus this one. So between these two, which one is more stable? Definitely this one is more stable, because these resonance structures have greater number of 4 covalent bonds present here. Actually, we are considering this and this position. If we consider these 3 also, then total number of covalent bond will be 3 plus 1 4 plus 3 7, and here 3 plus 1 4 plus 2 6. So as there is more number of covalent bonds, definitely it will be stable. Next, there is rule 3. In case of anions, the most stable structure is one in which the negative charge resides on the most electronegative atom. Okay, that means negative charge will be favored on the most electronegative atom, and positive charge will be favored on the less electronegative atom. Okay, we can consider one thing that on resonance structure, then you can easily understand. So in this case, there is negative charge. So when we draw the resonance structure, then what will happen? There is CH2 double bond, CH single bond O minus. Okay. So in this case, in one case that carbon negative and another case oxygen is negative. So which one is more stable? Definitely this one is more stable, and oxygen is more electronegative than carbon. So oxygen will prefer negative charge compared to the carbon. Next rule, we will discuss that canonical structures in which the octet of all atoms are fulfilled are relatively more stable. Here also we can take the same example, this example also. So here octet is not filled up, here octet is filled up. So each here oxygen is 8, carbon is 8, and this carbon is 8, but here this middle carbon octet is not filled up. So definitely this will be the most stable structure. Next, rule 5, the aromatic resonance structures are more stable and more contributing than the non-aromatic resonance structures having same number of covalent bonds. I can show you one example, then you can easily understand that this is the CH2 plus, and when you write the resonance structures, then you can easily understand double bond CH2, this one is the plus. Okay, so now between these two, this one is aromatic and this is not aromatic. Okay, so it will be more stable. Next, we can think about that another rule, that in a resonance structure having two dissimilar charges close to each other, okay, it's relatively more stable and more contributive. So similar charge should be placed at further at possible. Okay, at far away at possible, but similar charge should be very close. We can think about the Me3N plus. Okay, and next that CH double bond CH single bond CH2 minus. So here these two positive and two charge, one is positive and negative, they are far away. Okay, between 4 atoms. Okay, between 1, 2, 3, 4 atoms. But if we draw another resonance structure like this, Me3N plus CH minus CH double bond CH2. Here the dissimilar charge, that is plus minus, they are very close. So which one will be the major contributor or more stable towards the resonance hybrid? So this one is the most stable. So in this way, we have completed the resonance rules and resonance discussion. So you have to practice, and next day in next class we will discuss the hyperconjugation and other things. Okay, and DMNIS is also discussing the organic part. I think he is discussing the reaction mechanism like SN1, SN2 elimination. Okay, if I get time I will also discuss. Okay, so today up to this, thank you.